This is an example for half-life. The example states the half-life of radium-226 is 1,590 years. The two tasks we will perform are if a sample contains 200 milligrams, how many milligrams remain after 2,000 years? And the second task is about when will there remain only 10 milligrams of the radium. Implicit here is the task of building a model. So before we can do those two tasks, we're going to have to build a model. This first task will be evaluate the model, and the second task will be to solve an equation using the model. These are very typical half-life exercises. One of the other kind of half-life exercises is when you are trying to calculate the age given a current level. All right, so to build the model, there's a couple ways of doing this. There's kind of a shortcut and a not shortcut. So kind of the long way to build a model So this is without the shortcut. What you would do is you'd convert the information given into two data points, and that would be that at time 0 there's 200 milligrams, and at time 1590 there's 100 milligrams. Now this second point, this isn't given explicitly in the problem at all. This one is actually implicit using the first point and the half-life. You see there was 200 at the beginning, and so after 1590 years it will be half of that, which is 100. But from here you can create the model using the techniques outlined in another video titled Exponential Models Given an Initial Point and Another Point. I won't proceed from here. I'll let you see how to do that. The shortcut, kind of what speeds this up, is the following model. You take that the output, whatever variable you want to use here, we'll use m for mass. The output is the initial amount times 1/2 to the t over h, where a is the initial amount and h is the half-life period. So using the shortcut, we have our function is m equals 200 times 1/2 to the t over 1590. Now step 1 is, or task 1, is find how much mass remains after 2,000 years. So we'll just plug in 2,000 in for t. So this gives us m is 200 times 1/2 to the 2,000 divided by 1590. Punch that into a calculator and you get 83.63 milligrams. Now the second task is to find how long does it take for there to be 10 milligrams remaining. And we know this is a solving because of the question how long, so that's the time is unknown. Time is the input. So we'll solve 10 as the output equals 200 times 1/2 to the t over 1590. And this is an exponential equation. And so we proceed with the techniques for an exponential equation. Isolate the exponential by dividing the 200, and then take the log of both sides and continue. And where you will arrive is that t is approximate, well, I'll write the exact. All right, so t is equal to 1,590 times log of 10 over 200 divided by log of 1/2. And this is approximately 6,872 years. This kind of question might arise in an application problem where you're told that a safe level of this particular substance is at such a threshold. Let's say 10 milligrams is the safe threshold. So the question is, when is it going to be safe? That's a kind of question that might arise. That it's a fairly natural application of this kind of problem.